Today we're going to look at one algebra problem where we have xy in real number and satisfy this equation here, right? And we want to prove that x squared plus y squared equal to 1. In other words, xy as a point must be on the unit circle. There are actually many different methods of this problem. We're going to cover some of it. All right. So in the first one, we're going to use a parameterized equation for sine and cosine. Whenever you see 1 minus x squared, 1 minus y squared, you know that x, y are limited in the value, right? It must be between -1 to 1. And here, of course, naturally, you would be able to use, a variable transformation here. Let's say x equal cosine, y equal another cosine, because they're in this range, right? So let's do that. Let x equal cosine alpha, y equal cosine beta. Notice that we have the value between 0 to pi. This covers the full range of cosine, right? -1 to 1. Right? With that, we know that in this range, we plug in. This equation becomes this. Okay, here we assume sine beta, sine alpha, right, are positive. Okay, so square root is positive, right? But x could be negative here. Now, what you get is sine alpha plus beta equal to 1. Of course, alpha plus beta will equal to pi over 2. With that, you know that cosine alpha equals sine beta, right? Cosine alpha equals sine beta because alpha plus beta equal pi over 2. Now, with that, you know that x squared plus y squared becomes sine squared plus cosine squared of the same angle here, beta, that is equal to 1. Here is the proof. Okay, here is method number 1. Okay, so method number 2, we're going to use inequality. This inequality is true for all real numbers because x minus 1 square is greater or equal to 0, is non-negative, and then you move negative to xy to the right hand side, it becomes this very commonly used inequality. Okay, this is actually the base for geometric AM, GM inequality. Okay, but here we're going to look at that. Notice that equality holds if and only if xy equal to each other. Okay, so with this, let's look at this, this term here, right? The first term here, x. So let's apply the inequality that we know, right? So this is 2xy, right? So is less than x squared. The first term square, that's x squared. The second term square, this becomes 1 minus y squared. All right. Now you apply the second half. Same thing here. You add it together, add these two inequality together. You get this one less or equal to 2. But here you're saying that equal to 1. Equality holds, right? This is inequality, but you have equality. What is condition for equality? This x must equal to this. Y must equal to that. So the equality holds if and only if. That is, because since we have the equality here, we must know that this has to be true. In other words, x squared plus y squared equal to 1. That's the proof. Method number 2. Good. Let's move on. Method number 3. There is a well-known inequality. That is Cauchy-Schwaz inequality here. So here we're going to use that inequality. Here it says AB plus CD, right? So AB plus CD squared smaller than or equal to A squared plus B squared, C squared plus D squared. All right, that's good. So left hand side is what? Is 1. That's 1. Okay. That's S equal x squared plus y squared, right? So the inequality we're going to rewrite it as 1 less or equal to S. This is S. This is 2 minus S. All right. S is the value of interest here. Now this inequality, you're going to move everything to the left hand side. It becomes this one. This is of course the perfect square. S minus 1 square smaller or equal to 0. real number smaller or equal to 0 cannot happen with elective, so it has to be 0. In other words, s has to be 1. Right? So that's the proof. Okay? That's good. So let's move on to method number 4. Here we're going to use what is called inner product inequality. Of course, other people will argue this is identical to CS inequality. The method number 3 and the method number 4 are pretty much the same. Okay, so I'm not going to cover the detail here. Here, the idea is that this inner product is the magnitude of that vector is smaller than the product of the individual magnitude. So here's the vector, of course, one vector is xy, right? The 2D vector. The other vector would be the square root value. You plug in pretty much the same as method number 3 in terms of the steps. So we're going to ignore these details here. Okay, let's move on to method number 5. So here we have the equation with squared roots. We just square it, right? So of course you don't want directly square it. You want to move this term to the right hand side and then square it. Right? Let's do that. Let's square both sides, right? And then let's do some algebra here. Cancel certain term, combine certain terms, right? This becomes, this would cancel, right? Simplify it. You're going to become this, right? And further simplify it. Okay. So what do you have? Notice that this is again the perfect square. So this is the first term here. 1 minus x squared is the square root of 1 minus square. And this is a minus 2ab plus b squared. A squared minus 2ab plus b squared. So this becomes a minus b squared. What is a here? A is this one, right? So that would be the square. Of course, for the real number, this would happen only if y equals this or x squared plus y squared equal to 1. Alright, here's another proof. That's good. So let's move on. Number 6. We're going to consider the point to a straight line distance. You know that if I have a point outside of a straight line, and then the distance between the points to the points on the line is the shortest, and that is the distance. The point to line distance is the shortest among all the points on the straight line, right? That's a common fact. Let's use that fact in this method here. So what is a straight line equation? Okay, so since we have xy here, we treat them as some value, but let's treat this straight line in what is called ST plane. In ST plane, I have this equation here, something times s plus something times t equal to 1. That's going to be a straight line in the plane x. ST is going to be a straight line like this. Okay, and here of course for any point p x y, if you let s be x and y, that would be a point on this straight line, and we claim that OP, right, the distance here, is going to be always greater or equal to the point to straight line distance, because this d would be shortest among all the points on this straight line. Right, so we're going to do that. So what is OP? What is D? Right, so we have here, this is a setup here, right? So this is a straight line, and then the distance D from this origin to that is going to be given by this this inequality here, right? That just makes sense. And now we just plug in the numbers, right? For D, in this case, because the equation is here, it's also going to be 1 divided by this, square root of, the sum of squares here. So this happens to be 2 minus s. Again, s is the value x squared plus y squared, right? So that's a D. What is OP? OP is very straightforward. OP is just, square root of s, right? X squared plus y squared. So we have this inequality here. So let's look at this inequality, right? Let's square both sides. You're going to get this. It's very similar to what we got earlier in another method, right? So, and further, expand, you have this inequality. So s has to equal to 1. All right. In other words, that's the case. That's the proof. All right. I think we have covered enough method for different way of proving the fact that x squared plus y squared equal to 1. So let's before we go, let's cover another one. In this method, we're going to use directly some algebra manipulation here. So we have this inequality. We're going to start from there, right? So we're going to notice that here we're going to multiply 2 and move things around. It's going to be this. We're going to introduce some new terms here by utilizing this special form here. We try to complete the square. Okay, how do we do that? So we're going to create some terms here. 1 minus x squared and plus x squared will cancel. 1 minus y squared plus y squared. This y squared will cancel. So this is equivalent to number 2, right? This is 2 related to this, 4 terms here. Now, and these 4 terms, you're going to combine this with this one to be complete the square. Okay, so you're gonna rearrange into these 6 terms here, right? The first 3 terms is a perfect square. The second term is a perfect square. So what we get is perfect square plus perfect square equal to 0. For the real number, of course, individual term, both terms has to be 0. In other words, this has to be true and that has to be true. Both equation tells you that x squared plus y squared equal to 1. Okay, that's pure algebra method, right? So that's method number 7. Now, how about other methods? That's your job to figure it out. Method number 8, 9, and 10. All right. So please comments below to share your method. In addition to what we introduced here. All right. So hope you like the video. Please share and subscribe.